Hello, you all. This is Verily Berry Jr., and I'll be doing a some reading of quantum mechanics. So I figured I'll start a little series reading through the textbooks I'm working on right now, and as I make my notes, and maybe somebody be interested in going through that together. We'll see how it goes. Um, I'm not on camera at the moment. I have my uh, notes and textbook up, but sure I'll be on another time. So I've actually started through this book already. I'm getting a little bit of reading done ahead of time. And where we're at right now is on 1.4 normalization. Just briefly, let me share my links. Let me get the stem one up. So if you want to go to a Discord server, my Discord link is there. This, of course, is my YouTube channel. If you have x.com, there's my x.com. And also my Patreon if you want to show some support, sign up for tutoring or anything like that. So let's go back to the book. And this is Griffiths, uh, Introduction to Quantum Mechanics 1.4 Normalization. We return now to the statistical interpretation of the wave function, which says that, right? So going back to equation 1.3, which is up here somewhere, right? This is equation 1.3 here. Brown's statistical interpretation, which talks about how the probability of finding a particle from one spot to another is my first quantum professor called mod. So basically this is mod squared since this probability density is squared. So we're going back to that. So we have right, so this is the probability density of finding a particle. Point x and time t. And he says it follows from equation 1.16 that the integral, so basically the integral of psi squared over all x, so this would be negative infinity to infinity, or whatever is the full range that a particle would be in, like if the particle is in a box of this, must equal 1. And this goes back to the discrete example, like if we have, for instance, like a pie, you have a pie, and you cut that pie into 3 pieces. So the way I cut it here, we have 1/4 plus 1/4 plus 1/2, and we know that's going to equal 2/4 plus 1/2, or 2/4 plus 2/4, or 4/4, which is 1. So it's sort of like each of these parts of the pie is a probability, and all the different parts of the pie have to add up to 1 pi. So by the same token, all of the probabilities of a particle being somewhere all add up to 1 because there's 100% probability that the particle is somewhere. is the idea. And that's what they said, the particles got to be somewhere. So then they give equation 1.20 as, it's pretty much this right here. And I forgot my dx. So they call this equation 1.20. It says without this statistical interpretation, without this, the statistical interpretation would be nonsense, as we just pointed out here. Without the fact that all the different probabilities have to add up to one, the statistical interpretation wouldn't make sense because the particle wouldn't be somewhere with 100% probability. So, and as a reminder, I'm studying ahead to take this class in the fall. So, you know, sort of learning it together. And you can see how I do my notes. I think they're pretty, they work for me. Next paragraph, however, this requirement should disturb you. After all, the wave function is supposed to be determined by the Schrodinger equation. We can't go imposing an extraneous condition on psi without checking that the two are consistent. Well, at a glance at equation 1.1, and I'll click that. Right, so this is 1.1, which is a Schrodinger equation. I'll just write that into to have it there for clarity. So I h bar, the derivative of psi equals negative h bar squared over 2m u squared psi over x squared plus potential psi. Make sure I didn't make a typo. I h bar, the partial derivative with respect to t of psi. And just in case, let me make this a capital psi since that one is capital. And now we have negative h bar squared over 2m, the second derivative with respect to x of big psi, plus the potential in psi. And this is equation 1.1, so ironically they started with the Schrodinger equation. So the earlier parts of the book, I should have read it a while back. I'm picking it back up before class comes. So this is a reminder of what the Schrodinger equation is. So now to go back to that part. Well, at a glance at equation 1.1 reveals that if psi x of t is a solution, so too is a psi x of t, where a is any complex constant. All right? So looking at this seems to suggest that because in the Schrodinger equation, this I h bar is in the front. If I took the first derivative of psi, whatever that derivative is, so basically d over dt of psi would equal I h bar, and then whatever this ended up being over dt. So that's what I'm understanding that to mean, that the psi would have some complex component that the derivative will cause to pop out of the derivative, much like if you have x squared and you took the derivative of x squared with respect to x, you end up with a 2x. It's simply that in the case of Schrodinger equation, I guess technically this will be if we call this C, this would be basically be our C, and this will be X. I guess you can say dx of f of x. So I guess this is similar to that, where the C pops out in front. Slightly, because we still don't have x squared. So I guess we would have to do something like e to the x to make it be sensible, like e to the x squared. Does that do it? Yeah, I think that'll do it. Then you end up with uh, e to the x squared, and then you'll still have to take the derivative of the x thing, so that'll give us 2x. And if we call this c, then you have c. Uh, yeah, I guess I'm not thinking of a good example, so I guess we'll have to get there. What we must do then is pick this undetermined multiplicative factor so as to ensure that equation 1.20 is satisfied. All right, so we need to pick something to make sure that this does in fact equal 1 over all values of x. This process is called normalizing the wave function. For some solutions to the Schrodinger equation, the integral is infinite. In that case, no multiplicative factor is going to make it 1. The same goes for the tribute solution psi equals 0. Such non-normalizable solutions cannot represent particles and must be rejected. Okay, so that seems important. Only normalizable only normalizable solutions to equation 1.1 can represent particles. And must be rejected. Physically realizable states respond to the square integrable solutions to the Schrodinger equation. And it gives us a reference. So sometimes this thing wants to highlight rather than actually click the link. There we go. Evidently, psi of x and t must go to 0 faster than 1 over square root of the absolute value of x as the absolute value of x approaches infinity. Incidentally, and this is, I'm reading the footnote here. Incidentally, normalization only fixes the modulus of A. The phase remains undetermined. However, as we shall see, the latter carries no physical significance anyway. So, I guess we'll see what that's talking about momentarily as we go along. Right? But wait a minute on this paragraph here. Suppose I have normalized the wave function at time t equals 0. How do I know that it will stay normalized as time goes on and psi evolves? You can't keep renormalizing the wave function, or then A becomes a function of t, and you no longer have a solution to the Schrodinger equation. Fortunately, the Schrodinger equation has the remarkable property that it automatically preserves the normalization of the wave function. Without this crucial feature, the Schrodinger equation would be incompatible with the statistical interpretation, and the whole theory will crumble. This is important, so we had better pause for a careful proof. Okay, so now we're doing a proof that Schrodinger, Schrodinger's equation preserves normalization. And we on page 14 of Griffiths, even though I think the digital version may not quite match the book if anyone happens to watch this and have the paper book, but should be very close to it. All right, so it says the first line, d over dt of psi negative infinity to infinity, and we have our probability density. And now notice that he has, maybe I'm just in the habit of doing two lines. Notice they have one line, but I'm sure that's not the absolute value, that's the magnitude. That's those two squared. So all we did there was just bring the derivative inside the integral. And it says, note that the integral is a function of t. So I use a total derivative on the left, but the integrand is a function of x as well as t. So it's a partial derivative on the right. So apparently this entire thing here, the integral itself, capturing the entire thing, is a function of t, whereas this integrand here is a function of x and t, right? So we have, note that the integral is a function of only of t. Let's call derivative. Okay, the product rule. So what we're going to do is do the product rule derivative of the inside. And this seems to point towards the uh, sort of what magnitude sort of idea I had of this, but I may have to come back and adjust that. So that squared equals the partial derivative of t of psi equals. Now this just to be clear represents, I'm sure, a the what do you call it? They're basically orthogonal to the other one. Basically, the imaginary part of it, the sign is swapped. I forget the exact name, but I read it earlier uh, in the book. So why don't we scroll through and I could find what that term is to make sure I keep that in mind. I'll scroll back to that part that had the initial giving of the Schrodinger equation. What is that word? It's on the tip of my mind, but it's not quite coming. Maybe we'll farther back. In the preface, nope. What is that word? Well, sure, I'll find it along the way. Remember the exact word that so I'll come back and add this term, right? So this equals psi. All right. So what we're doing here is doing the chain rule, where we're taking the derivative of this one and leaving the one on the left alone, and then taking the derivative of that one and leaving the one on the right alone. So the book left the one on the left alone first. So I have to take the partial derivative of the right one. And then we have plus, basically the product rule. Now I'll take the partial derivative of the left side, the one with the star on it, and then I'll leave the right one alone. Now the Schrodinger equation says that, right? So basically it's just rewriting the equation. It looks like, okay. So I notice it looks like on this equation, they looks like they multiplied both sides by h bar squared. And by the way, just in case it's not clear, h bar should equal h over 2 pi, if I remember right. Right? So let's write down that next one. We have partial derivative of psi over partial derivative of t equals I h bar over 2m. Partial derivative squared psi over x squared minus I over h bar v psi. And hence also take, that's the word, complex conjugate. Right? The complex conjugate is the one with the star. Hence also taking the complex conjugate of equation 1.23. Right? Uh, I probably should refresh myself on the earlier part there because I don't exactly remember where the psi in that form came from. And this thing isn't scrolling. Let me see. There we go. might be easier to look back at my notes. And there's my note. I did remember that correctly. That h bar is h over 2 pi. Here's the complex conjugate on the left. It's about probabilities. Seems like that's just a given. Uh, I don't recall it being necessarily derived of how. So basically, what does psi have to come from to make that? Let's go back to where I was. One detail I noticed, by the way, is negative on the non-complex conjugate one and positive on the complex conjugate. Uh, also noticed that I missed it the first time, but there should be a negative here. So basically, if you notice for the complex conjugate, it's the same exact equation, except there's a complex number here. That number became negative, and there's a complex number here with a negative on it, so that one became positive. So the complex conjugate of the term is simply making each complex term swapping the signs. So swap plus and minus for the imaginary number. Uh, right. So that's 1.24. Thus, for 1.25, it says partial derivative with respect to t equals I h bar 2m. Right. So we have the partial derivative of the magnitude of psi, and this basically is the same thing we had up here, the probability density. I know that there's the book left off the x and t, which they do sometimes, but just to clean up the writing. But perhaps it's a good reminder to remind myself that there's actually the full psi with the x and t. So psi x of t magnitude squared equals I h bar over 2m. And The whole thing has an IH bar over 2m psi complex conjugate second partial derivative. Okay. So the first derivative with respect to t is 1.22. Seems to be there's some details missing. Like where is it coming from that psi equals this? So I don't recall that being explained. So scrolling through my previous notes, we have the solution to the Schrodinger here. Psi of t. This is the Schrodinger equation, which is 1.1. And then we go straight into the statistical. So pretty sure I would have missed that. So we have Schrodinger equation here. H bar is the Planck constant divided by 2 pi, which is this. I had that written there. You go into the statistical interpretation, which says that psi minus squares gives the probability of finding the particle at x at time t between A and B. Is this there? I have that here. And we have that the probability is the area under the curve of psi. So psi squared, the probability density is on the x-axis. Just like y could be on the x-axis. And x is the x-axis. Psi mod squared is the y-axis. Psi mod squared is the graph. And thus the area under the curve between A and B gives you the probability between A and B. I notice this is not showing my mouse. Let me see if I can make sure my mouse is showing. Well, let's all fix that later. And it's going into different types of uh, or ways of looking at quantum mechanics. Electron interference, probability, which is what we were talking about earlier. Give a brief recap on how the probabilities add to 1. Yeah, I don't see where they explicitly said that the Schrodinger comes from that. So this is all one of the benefits of having classes for these textbooks. Are primarily designed to have somebody pointing out some things so you're not necessarily studying it yourself. But we shall march on. And we'll take as a given that whatever psi is, so the idea I would say then is whatever psi is, when we take the first derivative of psi with respect to t, it has to equal I h bar over 2m, the second derivative with respect to x of whatever psi is, minus I over h bar, the potential, and then psi. So whatever psi is, we need to find the psi that solves this equation. And then whatever the complex conjugate of psi is, we need to find it such that this negative I h bar over 2m partial derivative with respect to the complex conjugate of psi over psi x squared plus I over h bar v psi is also met. So perhaps it's not so much where these equations come from in a sense, except for the fact that the Schrodinger equation, the only way it works is if our psi has this configuration, I guess you can say, where whatever psi we pick, it has to solve this. So thinking about it that way, if I go to equation 1.25 now, we have the partial derivative of mod squared. And we know that the partial derivative of mod squared from the previous page, the partial derivative of mod squared is the partial derivative of a complex conjugate times the time side, which is this. So that means I can take the partial derivative of psi squared from here. It looks like what we're doing is simply plugging this into the second part. That's what I'm seeing here. So therefore, the partial derivative of psi squared equals I bar. So why don't we, I'll add some steps to this thing. I think I see what they're doing now. I'll add some steps to this thing. So the partial derivative of psi squared, again, that's the repeat of that. That is the same thing as the partial derivative of t. So we write that complex conjugate times psi, and that equals psi complex conjugate times the partial derivative of t plus the partial derivative of the complex conjugate and psi, right? So now that we have the partial one here, I can plug that in. So it seems like we're saying this is the complex conjugate still, and partial derivative is this. So basically all I did on the earlier part, I just took this line right here and rewrote it basically. Took this highlighted part here, I rewrote it here, that's psi mod squared. This is that part repeated, and this is just filling this back in. But now I have what these are. So this value is this, and this value is this. So now I'm just going to plug that in, see how it works. So instead of partial derivative of psi, I'll actually plug in what that is to solve the Schrodinger equation, which is the sort of rationale I'm going with it at this point until we get more details. All right. And then we have plus. So I'll put the one in green here, which is negative I h bar over 2m partial squared of psi complex conjugate over partial derivative of x squared plus I over h bar v x. All right, so that seems good. And it looks like all the book data at this point was just distribute everything properly. All right, and move some things around. So what I'll try to do is see if I can simplify that and get the same thing if I'm seeing this properly. So all of this should simplify to what the book has. So let's see if we can do that. So what would this leave me? We have a pulled IH bar with 2M out front. So actually, let me just write this again and distribute some things. And I might be leaving out a multiplier. What multiplier am I leaving out? Uh, ah, I'm leaving out the regular psi on the back end here. All right. So I'm trying to look at this to see what's the most convenient way to simplify this and pull everything out. Right? Why don't I just write it out? So we would have, if I was to distribute this across both of these, this would be I h bar over 2m partial squared psi over partial x squared psi minus I over h bar. And then we have minus 2m squared psi squared big psi plus I over h bar psi squared. Right. So looking at this, we have a second derivative of psi squared next to a complex conjugate does not have a derivative. Then we have a complex conjugate second derivative besides something that does not have a complex conjugate. So that seems right. We have the psi squared. So we have a complex conjugate and a regular. So let's see if I mix something up here. So my psi of t is I over h bar 2m, second derivative psi over partial x squared minus I over h bar potential psi. That seems right, the 1.23. And then we have psi over dt equals minus I over h bar 2m partial derivative of psi, second derivative to the square to the x plus I over h bar v psi. All right, so this is where I left something out right here. Details. So I was missing this. That's the complex conjugate one right there. So what that means is this is complex conjugate squared right here. Oh, it should be squared because this is actually this one here. Oh, okay, I see. So this one is not, and this one is the one that would be complex conjugate right here. Here we go. Now we're getting there. So that one, I noticed that there was a pattern, like a uh, symmetrical pattern going on, but that it was broken. So that would explain it. All right. So to look at what we're doing here, I have the yellow part inserted here, and the green part inserted here. And then all I did was distribute the uh, the psi, and maybe it'll make it clearer if I put. No, this should be fine. So I have a psi and the psi complex conjugate, psi and a psi complex conjugate. Just one is plus and one is minus, because there was a negative right here, and everything looks good. So if I was to continue uh, distributing these, we have, so making it like the book has, I can start with pulling out the H bar over 2m, parentheses, and these two things have the H bar over 2m right here. So that'll be H bar over 2m and psi, to put it in the same order of the book, psi complex conjugate first. Our H bar is already pulled out, and then partial derivative with respect to psi. I'll make that a bit neater. Partial derivative squared with respect to psi over partial derivative of x squared, and minus the other one that has the I bar over 2m. So that's going to be partial derivative squared of psi star over partial x squared and psi. So that's the uh, first part there. And as you can see, these things cancel out. So you have a plus and a minus I over h bar potential psi complex conjugate times psi plus minus, where they cancel. So how are we getting there? And it looks like they did one more thing. Okay, I see. So if we look at this, we can say that, all right, let me write this in red. So this term here, partial derivative squared of psi over partial derivative of x squared minus partial derivative squared of complex conjugate over partial derivative of x squared psi. So it seems what they're saying is this is the derivative of something. So I'm remembering this from the first time I went through this class. What do we have? Partial derivative of 1. So for instance, if this was partial derivative with respect to x of complex conjugate and partial derivative of psi minus Oh, there's something, there's somewhere I'm vaguely remembering where this is equal to the derivative. And I can see it in the book. I mean, the book is showing it, but I want to understand how they got there. So basically, this part here is showing that that's a derivative of that, but let me make sure I'm clear how. Well, it looks like I'm gonna be able to backtrack it. Actually, I was pretty close. So they have that there. Yeah, it was actually pretty close. Then you have the partial derivative of the complex conjugate over x. So how does this work? If I did that, I would have to do the chain rule. So that would equal, I'll leave the left one alone, and then it'll be partial derivative of this plus, then I take the partial derivative of the complex conjugate, and then I leave that one alone, minus this whole thing. So I have to take the partial derivative of the left side. I'll start with the left side. So this will be squared. Uh, and then I'll leave the right side alone. Plus, now I'll leave the left side alone. Squared. And then take the partial derivative of x of the right side. So when I distribute this negative sign, that will give me the complex conjugate partial derivative squared of psi plus partial derivative of the complex conjugate over partial derivative of psi minus partial derivative squared of the complex conjugate. Distributing the negative sign, then is minus the partial derivative of the complex conjugate over partial derivative of psi. As we can see, we have a similar situation where these two are the same with different signs, so they cancel out. The partial derivative, the single partial derivative term cancels out. So then we're left with the complex conjugate times the partial derivative squared of psi with respect to x minus the partial derivative complex conjugate squared psi. Right, that looks good. So this allowed us to take the next step and say that we're going to basically reverse. Like in other words, we have this here. I'll use orange. So we have this here, which is this, and that happens to be the partial derivative of this part here. So I can say I h bar over 2m partial derivative with respect to x of psi complex conjugate minus psi. And it looks like all the book did was just pull out the derivative since it's not affecting I over h bar. So then we have the final equation, partial derivative with respect to x, everything in brackets, I h bar over 2m, and psi complex conjugate, partial derivative over x minus partial derivative with respect to x complex conjugate and psi. And the book calls this equation 1.25, right? So all we did was just work that around. So this term is the term that we pulled out to recognize it as the derivative of this. And then we actually took the derivative of that to test it. And sure enough, we do get back to the Ernst thing. So the Ernst thing is the partial derivative with respect to x of that. So then I just plug that in. And then I simply pull the partial derivative sign out and put that in front. And then we end up with equation 1.25 from the book. So the book just skipped a lot of steps. All right. So that seems like a good place to stop. And what I'll do is come back later or tomorrow or another day. And I may continue reading on my own from then, probably won't because I have other homework to do. So what I end up doing is I'll come back another day, either either a different day or later today even, depending on how my schedule goes, and we'll just continue from here. So I'm pretty sure I'll just continue this book here, and we'll continue working through this thing. And if anybody does watch have any questions, remember I'm learning this right now. It's not like a GED or anything else that I've this topic I've mastered. So I'm learning this, but we can try to help each other out. My Discord is linked here on my link screen. So join the Discord. We can talk there. Make sure you like and subscribe. If you need help on pretty much any physics lower than quantum, should be able to help. I'll be doing some learning assistant work on electromagnetism. So if you're in the EM class, this will be a great time to get help because I'll be working with that again. I worked on that in the spring. And there's actually some fun stuff. I'll be working with a great professor, the same professor I worked with in the spring. So I'll see you all later.